purpose of the sensor interface is to provide a flexible system for future and low power sensors. There is an I2C standard digital interface on board, which can be used with many current sensors and also makes it easier to develop sensors in the future. This is a low power system which provides a digital output. The analog system allows many different sensors to be read. There is a variable gain instrumentation amplifier on board, which increases the common mode rejection ratio. There is also a low pass filter which allows for the high frequency noise to be eliminated. There is a gain provided by the multiplexer which can be varied. This is done by different resistors providing different gains. There is a variable reference level which is provided by a DAC, which provides for a much wider range of sensors to be used. The microcontroller itself has an expandable memory via an SPI link to a micro SD card. A 10-bit ADC also converts analog input signals to digital. This is for processing and further communication out of the system. There is a power multiplexing module on board as well. This provides power for only one sensor at a time, which reduces the total power consumption. We can also disconnect any of the analog circuitry we need to in software to save even more power. All of this hardware will be demonstrated in the final integrated capsule. The sensor interface is connected to a development board, which provides a single set of connections to support up to 4 sensors.
We are using accelerometer as our inertial sensor in our capsule. We are using National Instruments USB I2C kit for our demonstration purposes. That includes 3-dimensional visualization, which is later implemented in a microcontroller for our end capsule. We take the measurement readings directly from the accelerometer using NI kit, and then which we configure to be reading plus or minus 8G, that corresponds to 256 discrete levels, which equates about 16 discrete readings per G. As you can see, when the capsule is tilted in single axis, you can see the tilt angle changing. As you can see, if the capsule is tilted in another single axis direction, the roll angle changes. We are able to measure the activity based on the G readings coming from the accelerometer, which we can determine walking, jumping, and idle positions. As you can see now, when the idle motion is simulated in the capsule, we can basically see on the screen that the patient's current status is idle. When the walking motion is simulated, the status of the patient changes to walking.